From text to knowledge, a hybrid framework to enhance semantic analysis using language model and heuristic. Team, Professor Fatma Amara and Professor Hisham as a supervisor, and Ahmed Hassan, me. Introduction. Natural language processing faces significant challenge in extracting nuanced deep semantic from unstructured text. This research addresses this challenge by integration two powerful methodology, the statistical power of pre-trained language model and the precision of human-defined heuristic rule. Paper statement. This paper introduced a novel hybrid framework designed to extract nuanced semantic information from general unstructured text. It integrates the statistical power of pre-trained language model with the precision and interpretability of heuristic rule written in traditional scripting language. Motivation and the challenge. Complexity of human language. Natural language is characterized as ambiguity, uncertainty, incompleteness that make it difficult to process. Number two, limitation of pre-trained language model. Model as a statistical relationship, but often fail to comprehend deeper context-dependent semantic. They can lack the interpretability required for high accuracy application. Drawback of rule-based system. Traditional manual created rule often can't handle the ambiguity of natural language, are time-consuming to create, and are not generalized across domain. Identified research gap. The absence of fully automated end-to-end framework capable of processing general natural language text to generate a comprehensive set of structured format with manual intervention. Leverage modern AI without sacrifice the precision. Our contribution, hybrid integration between large language model and heuristic rule, end-to-end automation, and interpretability precision. Related work, limitation of existing approach. Manual rule construction, domain dependency, lack of explanation, limited semantic depth, lack of integration between traditional rule and large language model. Framework goal. The proposed intelligent framework is designed to automatically convert natural language software requirement into formal UML representation. Our methodology built on multi-stage process. Number one, pre-trained language model like Spacey for initial text analysis and statistical extraction. Stage two, heuristic rule that apply to distinct symbolic layer to refine, correct, and augment the model's output. Stage three, multi-model graph that refined and integrate output are used to construct a formal structured semantic graph and UML diagram. Core component. Stage one, pre-trained language model. We choose a Spacey model and refine it by add layer of name of entity, customized layer of name of entity. Heuristic rule. This component distinct symbolic layer that follow the AI model. This separation allow work splitting. This means rule can be enhanced or corrected without needing to retrain the entire AI model. That save time and cost. Constructing layer 3, constructing multi-model graph. The final output from the statistical and symbolic layer are integrated from formal structured knowledge representation. This semantic graph and UML diagram become a machine-readable artifact capturing the deep semantic of the original unstructured text. This is the model architecture from layer number one, unstructured narrative input, go to Spacey model, customize it, and retrained Spacey model, then go to heuristic rule to get the annotation, the new annotation trained on it, to add a semantic to this annotation, then framework knowledge representation takes the output and generate semantic graph and UML class diagram as first step. Case study, like this is a sample of story. We generate it, and after the model, at left side, the semantic, all this slide is semantic graph of this story. So now I can represent unstructured text to ontology or semantic graph represented so I could be computer readable. Next graph is class diagram. The system generate class diagram, describe the story. When measure performance, I get precision 88 and 6, and the F score, and the accuracy and the recall. Conclusion: successful integration between scripting language and large language model, generate UML diagram and semantic graph, achieve high performance, and the most important point is end-to-end automation. There is no manual human intervention to reconstruct the story or the requirement to be structured or semi-structured. How we deal with ambiguity? Number one, pre-train the model to generate annotation suitable for specific domain. Number two, specific domain, because each domain has its keyword that illustrate it. Syntactic contextual analysis as a part of speech, it's implemented by a large language model or pre-trained language model. Heuristic for detection act like human brain for generate the semantic of the story. Future work, expand the new domain. The multi-layer we approve make us insert multi-domain and train on multi-domain, not specific domain. Human in loop make the user can adjust or correct the result generated by the model. Scalability testing, we can use multi-domain at this model because I deal with the English grammar. Anything in English grammar can be read. Any question?
Thank you for presenting your work. I think you provided an interesting framework composing of those three parts. I think in the case study, you moved so fast on the case study. Perhaps you showed us the output, the story, and the final output, the graph representation. But you didn't explain how did you go into the three parts. Because of the time. Now it's open for questions. So perhaps you can tell us about how did you go through your experiment into the three parts before generating the final. Yeah.
At first step, I use large language model, pre-trained the language model like Spacey, and fine-tune this model by new annotation to name of entity to be suitable to my current domain. So I make it generate a new annotation trained on it to make easy for heuristic rule to get the semantic from that. So I make new annotation for layer of name of entity at Spacey model. Then get the output to the Python script, each at multi-level, each level detect one semantic like adjective, probability, relation, objects, actions, actor. So heuristic Python rule takes the name of entity generated by the customized pre-trained model and generate Excel sheet describe this relation and the attribute and the object. Then go to the graph model, take this Excel sheet or make Excel sheet and JSON file. Make this Excel sheet and JSON file to be a presentation semantic graph and the class diagram. And there exist future work I work on it to make to work on requirement representation for software lifecycle. So I can make a class diagram and use case diagram and the class diagram and the semantic graph. So I make it multi-stage. So when I need work on new domain, I just make a new annotation if I need to the space model and retrain on it and the heuristic rule as it is. Or if I need to adjust only the heuristic rule, I let the retrained model as it is and work on heuristic rule written in script Python script language. The layer of generating the graph is static because there is no change at it.
Any other questions or remarks or comments?
Yes.
Yes, Professor.
Okay.
The problem that this solution is trying to solve. So what's the main problem that this solution is trying to solve? This is number one. Number two, this is something like a simple knowledge graph, something like this that can apply on different domains of knowledge, as you mentioned, or is it a pre-trained model and a specific type of knowledge?
Customized pre-trained model.
Okay, so what's the problem you're trying to solve using this?
First, the problem is manual intervention to the requirement representation for software. Because
So it's part of the software.
the last work,
development.
the previous work use formal,
Yes.
formal or semi-formal requirement to make the machine learning work on it to extract the semantic. There is no tool deal with the normal language.
Yeah, I understand. So what about the Arabic language in this solution? What about the Arabic language in this solution?
I start with English language because the grammar is easy. Arabic language need more effort and work to extract its semantic. English grammar, I can represent it by heuristic rule at Python, easy. So I can extract the semantic.
Thank you so much.
Thank you very much, sir. Allow us to present you with a certificate. Our next paper is titled Deep Super Resolution and Age Prediction for Brain MRI using SRCNN, a lightweight framework for high fidelity reconstruction and regression. The researchers are from the Egypt-Japan University.
ماشي، السلام عليكم. أنا أمنية. أنا وحنين زميلتي المفروض جايين النهاردة عشان نبريزنت البيبر بتاعتنا Deep Super Resolution and Age Prediction for Brain MRI using SRCNN. الأوتلاين بتاعنا
Is it
إحنا
possible
هنبدأ.
to present in English, please?
Sure.
If that is possible, I appreciate it.
I will use two. Okay. This is our agenda for today. Me and Haneen will walk through all the steps we did to reach our results. First, background and motivation. المين بروبلم هنا كانت انه احنا عارفين انه الام ار اي هي اكتر حاجه اكيوريت عشان ان احنا نانلايز البرين ستراكشر والايجنج بتاع البرين. فالمشكله هنا كانت انه الام ار اي سكانرز اصلا بتكون هاي، يعني غاليه جدا، بتستعمل 3 تسلا ماشينز. فاحنا عشان نحل الموضوع ده كمان المستشفيات اصلا بيكون فيها السكانرز بتاعتها بتكون مثلا لو ريزوليوشن، مش هتاخد كل الفيتشرز صح، فبالتالي الايدج بريدكشن مش هيكون اكيوريت زي الاول. فاحنا عشان نحل المشكله دي بنستعمل بايبلاين BSR-CNN. اول حاجه ان احنا بنعلي الريزوليوشن بتاعت الصور، بعد كده ندخلها على موديل convolution neural network عشان نستعمله ان احنا نبريدكت الايدج. المفروض بالطريقه دي يعني احنا بنديفلوب طريقه احسن من ان احنا نستعمل ماشينز غاليه جدا. حنين هتكمل معانا الميثود بتاعتنا، الميثودولوجي والداتا سيت، كل حاجه احنا عملناها.
دي البروبوز ميثود اللي احنا مشينا عليها بالظبط. احنا عندنا الام ار اي فوليوم. الام ار اي فوليوم عباره عن 3 دي داتا. اول حاجه لازم نعملها ان احنا نحول ال 3 دي داتا دي ل 2 دي داتا عشان اقدر اتعامل مع الايمجز. بعد كده بدخلها على الموديل بتاع السوبر ريزوليوشن، بعد كده بدخلها على الايدج بريدكشن. الداتا سيت نبذه بسيطه عنها، هي ICICIS برين MRI. هي فيها 600 structure TI weighted brain MRI volume. فيها collected from hospitals. هي عباره عن 1.5T and 3T MRI scanners. الداتا قبل ما ادخلها على اي موديل انا بحتاج ان انا اعمل لها بري بروسيسنج. اول بري بروسيسنج انا عملته للداتا هو السلايسنج. السلايسنج بتاع الداتا ان انا بحول 3 دي داتا ل 2 دي. بعد كده بعد ما بعمل سلايسنج انا لازم اختار بالظبط ايه السلايس اللي فيها الموست امبورتنت فيتشر اللي انا هحتاجها، وهو ال50 سلايس اللي بتبقى في قلب السنتر لكل فايل MRI. تاني حاجة بعمل image resizing and normalization. الريسايزنج بتاعي 128 في 128 أنا بخليه يونيفايد لكل الإيمج اللي عندي. بعد كده النورماليزيشن مينيماكس نورماليزيشن من 0 ل 1 علشان أخلي كل الداتا الفاليوز بتاعتها ما بين 0 و 1 تبقى كل سكيلبل واحد لكل الداتا عندي. ثالث حاجه اللو ريزوليوشن سيميوليشن. اللو ريزوليوشن انا بحتاج ان انا اضرب الموديل اللي بعده اللي هو الديب سوبر ريزوليوشن موديل. فانا محتاجه ان انا اقلل الريزوليوشن عشان اقدر اعمل ترين للموديل اللي جاي. او احنا عندنا 2 ديب نيورال نتورك عندي 2 اول واحد اللي هو السوبر ريزوليوشن CNN. السوبر ريزوليوشن بيمشي ازاي على كل الداتا؟ اول حاجه الفيتشر اكستراكشن، لازم يجيب من كل سلايس في الداتا الموست امبورتنت فيتشر اللي فيها. تاني حاجه النون لينير ماب. النون لينير ماب هو بستخدم فيها ريليو نون لينياريتي اكتيفيشن فانكشن. الاوتبوت بتاعها يا اما 0 يا اما اكس. الزيرو لو الداتا بتاعتي الانبوت نيجاتيف. تاني حاجة لو الانبوت بوزيتيف بيخليه زي ما هو، فده بيحسن لي الشاربنس بتاع الفيتشر ويطلع لي الداتا سوبر ريزوليوشن دي لأجزاء صغيرة من الداتا. تالت حاجة الريكونستراكشن. الريكونستراكشن اللي موجود في الآخر بوينت هو اللي بيبني لي الصورة الكاملة. يعني أنا لو مدخلة الإيمج 128 في 128 لازم الأوتبوت يبقى نفس الصورة، فالريكونستراكشن هو اللي بيبني لي الفيجر تاني بعد ما بخلص ان انا بعمل نون لينياريتي ماب. كده احنا عملنا الصوره بتاعتي طلعت بقت هاي ريزوليوشن. انا بدخلها على تاني موديل عندي اللي هو الايدج بريدكشن. الايدج بريدكشن ماشي بسيكونس ان انا بعمل ان انا باكستراكت الفيتشر اللي موجوده في كل صوره عن طريق 5 convolution blocks. كل convolution neural network followed by squeeze and squeeze. دي بتخلي اللاير الاخيره دي بتخلي الداتا ان هو الموديل يفوكس اكتر على الفيتشر، ما يركزش على فيتشر جانبيه مش ريليتد قوي بالايدج. تاني حاجه الادابتيف بولينج اند فيتشر فلاتنج، ده بيخلي لي convert entire feature map to single value per channel. اخر حاجه regression head ده اللي بيبريدكت الاوتبوت بتاع الايدج بتاع كل صوره عندي. فاحنا كده عملت ايدج بريدكشن في اخر الموديل. في عندنا جراد CAM ده هو عباره عن بيطلع لي صوره هيت ماب الموست امبورتنت فيتشر كانت متجمعه فين، ايه هي الاماكن بالظبط اللي في الصوره اللي ساعدتني علشان اعمل ايدج بريدكشن. الريزلت كانت الاوتبوت بتاعتنا كانت كويسه. الBSNR 30.45 دوت بيشوف لي الكواليتي اوف reconstructed image اللي طالعه لي من السوبر ريزوليوشن. في عندي SSIM ده بيشوف الماتش ما بين التو images اللي هي جراند تروث اللي موجوده عندي في الداتا سيت والريكونستراكتد ايمج، فالاوتبوت الماتش ما بينهم 0.95، فده رقم كويس جدا للداتا بتاعتنا. اول صوره دي اللو ريزوليوشن، تاني صوره ده الاوتبوت من CRCNN، اخر اوتبوت ده الجراند تروث اللي موجود في الداتا سيت اصلا، فمن لو ريزوليوشن لهاي ريزوليوشن. ده الماتريسيز اللي عندنا اللي بتقيس الايفالويشن. فاحنا بنشوف هو عباره عن هيستوجرام، بنشوف ان التكتل بتاع الاوتبوت عباره عن الفاليو 30.5، وعند SSIM الفاليوز الاكتر موجوده عند 0.95. برضو دي عباره عن الماتريسيز، عباره عن برضو اشكال تانية ان الاوتبوت متكتل اكتر عند الارقام دي. الاوتبوت بقى او الايفالويشن بتاع الايدج بريدكشن كان في التست مطلع عند المين سكوير ايرور 2.35 والار سكوير كانت 0.96. ال 2D densely بلوت للايدج بريدكشن، اللاين الريد ده هو عباره عن الموديل طلعه، اللون الازرق هو عباره عن الجراند تروث الفعلي بتاع الداتا، الرقم الفعلي بتاع الايدج. تريننج لوس بنحاول ما بينه وما بين الايبوكس، كل ما بتزيد الايبوكس كل ما اللوس بيقل، وكل ما بيزيد الايبوكس كل ما الBSNR اللي هو التشابه ما بين الايمج ريكونستراكتد والاصليه بيزيد. الجراند تروث هو الهيت ماب اللي احنا بشوف الفيتشر الاخيره مظبوطه فين. Thank you.
Thank you. That's a very nice presentation on time. So, any questions from Professor?
Okay, maybe a small question. I know your work is image-based, الشغل على الصور. ولكن in the presentation you have mentioned there are metadata associated with the images. Have you made use of the metadata in your proposed work? الميتاداتا استخدمناها في حاجة في الشغل بتاعك؟
الميتا داتا كانت فيها values عن الايدج والجندر. انا استخدمت بس الكولوم اللي محتاجاه اللي هو عباره عن الايدج
only. So and you're making age prediction. يعني ما استخدمناش حاجه من الميتا داتا.
لا.
Third paper, ARIMA forecasting with LLM-powered multi-agent coordination for omnichannel retail KPIs. And Mr. Darian, presented by Darian Rees from Leroy Science Foundation, Ireland Research Centre for Software, University of Galway, Ireland. Welcome to Egypt, sir.
Hello, everyone. My name is Darian. Apologize, I lost my voice, so I am going to speak very, very slow. So, this project is presented by the Research Institute Lido and the company Kilkenny Design. It's a very interesting collaboration between academia and industry because we are implementing artificial intelligence methods in a real company. So this is the agenda of the presentation. Can you please, you can read it in general. We are going to present the general framework as an general overview. The infrastructure in GCP or Google Cloud Platform, and we are using Power BI as a front end. We are going to present especially the reports and KPI agent workflow and the pipeline that include several GCP models like BigQuery and Power BI to generate the forecasting. At the end, we are going to present some samples and to finish the evaluation metrics and the artificial intelligence risks and mitigations inside the company. This diagram presents the general pipeline. That is contains a few AI agents for the warehouse, social media, front of the customers in the company, and logistics agents and reporting and KPIs for the employees, the staff in the company. This company is in the retail sector in Ireland, has restaurants, e-commerce, and physical stores as well. So inside the company, we are trying to implement traditional machine learning algorithms like this time series, seeing as a regression problem. Sorry, as a regression problem, and AI agents using large language models. We are counting with a data warehouse with 4 years of historical data, mainly inventory, the warehouse transaction status. We have more than 5 sources of data that is collecting all unification and cleaning and pre-processing in the data warehouse. This is one of the AI agents that we are building in the company, specifically for the KPIs and reporting. Is sent every day in the morning, very early in the morning, 8 a.m. So the pipeline contains several steps. Initially, the first one happened 1 a.m. and the last one is 8 a.m. to deliver the reports. The traditional machine learning method is specifically for time series forecasting for the sales, profit, and task forecasting. So we have these steps in BigQuery inside GCP. This is one example of the final report. So this is the UI for the staff. The end user here are employees. This report is in production since April this year. And this one is in production since September. The second report is very interesting because we are presenting data and KPIs from different sources. This is another example. For example, we can identify in the decision-making meeting handmade soap gift set was the top selling item online, I mean e-commerce, 2 weeks in a row. So they can take actions with this specific category. The evaluation criteria is RMSE, the root mean square error to calculate the performance of the algorithm. And finally, we are working with the company is recent mitigations mainly aligned with the GDPR in Europe Union. So some examples are here, and the last one, I'm going just to mention the last one, is false output via attacks ensure accuracy. So we have double checks and validation use advisory training to verify info to avoid sharing unconfirmed content. Apologize again for my voice. I lost it yesterday. I hope you can read the rest of the presentation. Thank you so much. If you have any question, please.
Yeah.
Yeah, sure.
If you would like, I mean,
Risk mitigation in terms of compliant with the GDPR, the European Union General Data Protection, and also the security related to illegal access and things like criminal activities. How could you develop such a system inside the solution you have mentioned? This is number one. Number two is why did you choose Power BI? Because you were comparing two different solutions. Thank you.
Yeah, very good questions. Okay, the first one, we are solving the 90% of the problem with the GDPR with the infrastructure in Google Cloud. One example is we we have to save all the data in Europe, and Google Cloud Platform allows us to specify the specific region where we are saving the data and using the hardware and the servers. The second question is very interesting because we have many options for the front end, but in this case we have close to 100 reports generated for close to 20 staff in the company. But one interesting is that the staff doesn't have technical knowledge and they can drag and drop to move the columns and the rows, the filters very easily without any extra implementation.
Okay. Thank you so much.
thank you very much. Allow us to present you with a certificate of gratitude. Our fourth paper is a novel hybrid deep learning network for multimodal emotion recognition. The authors are from Banha University. Is anybody of them present? Mariam Al-Muhsin, Haya Usama, Professor May Salama, or Professor Sahara? They're not here. Right, we'll move to the fifth paper, which we have a multimodal spoken Arabic dataset collection for emotion recognition. Ms. Mariam Aslan, Ms. Basmala Hasham will be presenting. The co-authors are Professor Muhammad Abdul Majid Salim and Professor Nada Sharaf. They are from the German University in Cairo, Faculty of Media Engineering and Technology.
Good evening, everyone. My name is Basmala Hashim, and this is my partner and friend Mariam Aslan. Today we'll be presenting our work on building the first spontaneous multimodal emotion data set, specifically for the Egyptian dialect in Arabic. Our project addresses a critical gap, which is that Egyptian Arabic is one of the most widely spoken dialects worldwide. However, it remains severely underrepresented in ineffective computing and lacking resources that capture genuine real-world emotion. This is our roadmap for the presentation today. We'll briefly walk you through the motivation, research gap, and everything until the future work, starting off with the motivation. Now, imagine a voice assistant that can't tell if you're frustrated, or even a mental health application that cannot differentiate between your sarcasm and your sadness in your own dialect. Now, this is not just an imagination or a future problem. This is the reality for millions of Egyptian speakers today. The reason is a critical gap in a critical data desert. Current AI is mostly trained on English data. So, and to a lesser extent on scripted Arabic and formal Arabic. However, emotion is spontaneous, it's cultural, and it's deeply connected to dialects. Our motivation today is to break the technological wall, which means that the AI fails to serve a huge population effectively in areas like the personalized services, empathetic technology, and even accessibility tools. And our goal today is to break this technological wall by providing the missing key, which we believe is a real spontaneous data set for emotion, specifically for the Egyptian dialect. For the research gap, our analysis of existing research or existing resources revealed a consistent set of limitations. All the Arabic data sets for emotion are heavily scripted, resulting in fake or unnatural expressions. They're mostly monomodal, focusing on either the text modality or the audio modality, mostly on audio modalities. Crucially, they predominantly use the modern standard Arabic, which is not a language used in any Arabic region and therefore is not emotion related much. So the result is a complete absence of a resource that captures authentic multimodal emotion for the behavioral Egyptian. So for our related work, globally, benchmarks like the three datasets, the English datasets, have set high standard for multimodal emotion data. However, they're all in English. There are evolving, emerging datasets, however, for the Arabic, like the three we see on the screen. However, they are still quite limited as they lack dialectal diversity. They're quite small on scale, and they are not all multimodal. So in response, our core contribution is to build a multimodal spoken Arabic dataset for emotion recognition for the Egyptian dialect. We started by collecting some TV videos from TV shows, interviews, podcasts, etc. Those clips were then segmented, transcribed, and then annotated using the 7 emotions, which are Ekman's 6 basic emotions plus the neutral class. Furthermore, to establish a benchmark and prove its utility, we've conducted extensive baseline experiments with models for all modalities. This is our data collection pipeline. We started by creating grow videos from YouTube videos for the Egyptian talk shows, interviews. Like I said before, we then extracted high quality audio, and after that, we generated accurate transcripts using Whisper AI. After that, the clips were segmented into further manageable units, all during the pre-processing step. After that, all the modalities, the 3 modalities, text, video, and audio, were independently annotated by trained evaluators. Then for the feature extraction, we had to extract features for the model training, specifically for the audio modality. Last but not least is the validation step, which we're about to walk you through step by step for all modalities.
So after our data set is complete, we then move to the final stage, which is the validation stage, where we validated the 3 modalities, the text, audio, and video. So starting with the text modality, we first used a model called Airbird, but we achieved, unfortunately, a very low accuracy, which is 19.86%. And this is due to the fact that it is a modern standard Arabic, therefore it fails to understand dialects. And also it lacks a neutral class, which is a very dominant class in our data set, as we focus on real and natural emotions. That's why the misclassifications were a lot. So we moved to use another model, which is DeepSeek. DeepSeek is a large language model, and we achieved a better accuracy of 51.37% with it, as it's better generalization, as it uses zero shot. That's why the performance improved. Next is the video modality. We tested our modality on two models, which are DeepFace and FAR. Both models are pre-trained on scripted data. We achieved a lower accuracy of 32% with the DeepFace and around 49% with the FAR. But the problem is we face some challenges with both of them, as both of them find it hard to detect subtle facial expressions. While DeepFace cannot process only static images and not image sequences, while the FAR has struggles with the varying camera angles. And the last modality is the audio modality. We first tested it on a wave-to-vec model, but we achieved a low accuracy of 22.6%. And this is due to it not being able to differentiate between the voice of the speakers and the background noise. And also it lacks cultural context. Therefore, we decided to train our own model, custom CNN, based on an Egyptian Arabic audio dataset. And we did that because all of the pre-trained models underperform, and that's why the training was necessary. And we achieved a better accuracy of around 45%, which is more than double the accuracy we achieved with the wave-to-vec. And for our final data set, we collected around 150 segments, and for each segment, its duration ranged from 2 to 23 seconds. We try to ensure that only one speaker is visible per segment, with clear auditory emotion cues. And for the distribution, the most dominant emotions were the neutral and the sadness emotions. And this happened because we focus on real and natural emotions, and that typically reflects how people typically feel in their daily life. So to conclude, what we basically did was we refined a complete data collection pipeline for the three modalities, audio, video, and text. And it's specifically for emotion recognition. We then used this pipeline to collect our data set, and we achieved a final accuracy after fusion of the three modalities, which is 50%. So finally, for the future work, specifically for the near-term improvements, we want to expand the data set beyond the 150 segments that we already collected. We want to add more spontaneous real-life speech, and we want to improve training via domain-specific fine-tuning. As for the long-term improvements, we plan to include more dialects other than the Arabic Egyptian dialect, which we already collected. We want to model cultural and linguistic emotion differences. And last but not least, we want to build more generalized emotion recognition tools across the Arab world. Thank you. That's it.
Thank you very much. Any questions or comments from the audience, please? That's fine. Please, go ahead. We're lucky to have you here with us, sir.
Thank you so much. First, how did you measure the accuracy of whisper? Because whisper is not accurate in Arabic in general, not the Egyptian dialect. This is number one, the accuracy of this model. Number two is the infrastructure that you are using to train them. I didn't mention.
The details of the model training.
Yes.
Panel?
You have an answer? You have an answer for the question?
Yes.
Discuss together first.
Thanks. Well, regarding the Whisper AI model, we personally went over all the transcripts.
Oh, we did manual checkup.
Yes, for every clip, for every
Yes.
Yes, yeah, we had to recheck because there is no dialect-specific kind of transcript model that can transcript the clips and audio, so we had to manually recheck every clip again for accuracy. And your second question was for
The infrastructure that you used to train the model.
Actually, it's a deep learning model based on random forest classifier.
Okay, so what
We
about
used
the,
a pre-collected data set from
the
one of
hardware
our
that
one of
you
our
are running
colleagues.
the model on? So what's the specification of the hardware?
specifications.
كان يعمل
Did you use any specific GPUs, something like processing unit? This is based on CPU or GPU?
based on CPU or GPU?
Yes. GPU?
GPU.
Okay. You have to mention the technicalities of these things.
Yes.
Thank you so much anyway.
Thank you.
Any questions from the panel?
I want to ask one question. You said you collected data, right?
Right, yeah.
I want to ask about data annotation. How did you give labels for the video, for the videos you collected?
We were using the 7 emotions, which are Ekman's 6 basic emotions plus the neutral class. And per clip or per segment, we had at least 3 annotators annotate the clip or the segment. And if there were any kind of differences, for example, say each one had different view or different emotion per the segment, we then had like some kind of a meeting per that segment, so that we can decide or agree on one emotion for this segment.
Yeah, and we did also independent annotation for each modality.
Can you repeat the last sentence?
I said we did independent like annotation for each modality on its own.
We annotated each modality independently. For the text, we annotated text alone, and then video alone, and then the audio on its own.
Perhaps I missed something. I was just going to ask the same question. This means you have made this per segments, but is the annotation done manually, or there are some automatic technique?
Yes, it's done
manually. And is this just your personal judgment?
No, we have collected annotators. It was like a kind of within our friends, and we trained them, and we had like some scripts, guidelines for the annotation. They followed the guidelines, and according to those guidelines, they annotated each modality for each segment. They were trained on it by the guidelines first.
And this has been done once, or did you repeat this by several times to get a good estimate for generating the ground truth?
Well, it was
once.
Oh, okay. My second question is, how big is your data set that you collected?
We have
Because
around
in your work,
150
you work with the deep learning and large language model. Perhaps the percentages that you have recorded have some influence with the data set that you create. How big is your data?
It's around 150 segments.
I can't hear.
150 segments. 150.
150? 150?
Yes, we're
Not
planning to
150K.
expand it.
150. Okay, but perhaps this makes some sense for the results that you have. Okay, maybe when the data set is more.
Yeah, that's why in the future work we
makes
plan to
an
include
influence
more.
for your experiment. Yeah. Okay. Thank you.
I'm looking forward to seeing the future for a reason. Some classifications classify different Arabic, what you call dialects, into different languages. So I'll be looking forward to either verifying that or disqualifying that statement. So good luck. Thank you. And we need to present you with certificates.
Thank you.
Last but not least presentation towards accurate water quality prediction using attention-guided deep imputation models, presented by Marwa Hilali, co-authored by Professor Shireen Radi, Dr. Muhammad Mabrouk, Professor Mustafa Arif, and Professor Ahmed Al-Awadi. Professor Al-Awadi is from the Institute of Environmental Studies and Research at Ain Shams. The other colleagues are from the Faculty of Computer Information Sciences at Ain Shams University.
Hello, my name is Marwa Hilali. I'm here to present my paper towards accurate water quality prediction using attention-guided deep imputation models. So the goal of this paper, the goal of this work is water quality prediction, accurate water quality prediction. So why is accurate water quality prediction important? Because water is essential for life. It's needed everywhere. It's needed for drinking, it's needed for agriculture, it's needed for industry, it's needed everywhere. So to be able to accurately predict water quality in different water bodies and different locations everywhere around the world is extremely important. In order to be able to efficiently perform water quality prediction, we need large, diverse data sets, and we need those data sets to be complete. But one of the main issues of water quality data sets is that they have very high missing rates, and that usually happens because of many possible factors. For example, sensor failures, human error, or any environmental factors, any disaster that would happen that would cause maybe the sensors not to work, and that would cause missing data. So this is very common in water quality data. But unfortunately, naturally, any missingness in the data would cause a reduced model reliability and performance. So one of the methods that we can use to resolve the issue of missingness in water quality data is imputation. So imputation just means to fill the missing data with other values. Those other values could be various things. So there are different types of imputation methods. There's statistical imputation methods, there's traditional machine learning imputation methods, and there's deep learning imputation methods. They are different levels of imputation, and they get more sophisticated as we move up. So before we jump into the imputation method that we used, we need to understand the qualities of water quality data. So water quality data, first of all, it's multivariate, so it consists of multiple variables, and it's usually time series data, so there's a time aspect to that data, and there's also a spatial aspect to that data. And all of these features interact together in terms of time and in terms of space. As I said just briefly now, there are multiple ways to perform imputation. So one of the common ways that we are going to, this paper selects or uses 3 different types of imputation. So the very first basic type of imputation, which is statistical imputation, we're using median imputation. And for the machine learning imputation, we're using KNN imputation, which is K nearest neighbors. And then the important aspect of this paper is the deep learning imputation, which is called SATES. We're using a model called SATES to do that. SATES stands for self-attention for imputation of time series, and it's based on attention and transformers. And we'll review what happens inside of it very briefly. So our framework, it's called the IPM. It stands for Dual Imputation Prediction Model. It consists of 2 phases. So the very first phase is the imputation itself. So as we see here, the data set at the very beginning, it has missing data. The black part is missing data. And it enters SATES. And SATES is our deep learning imputation method. And it does the imputation, and then we have an output complete data set with no missing data anymore. So using SATES, our data imputation model, is the first half of this framework. The second half of the framework is, once we have a complete data set, we can now predict water quality. And to do that, we experiment in this work with multiple types of deep learning models. And we will review each of these models in just a little bit as well. But the important thing is that the framework consists of these 2 different phases, the imputation and then the prediction. So the data set that we use here in this work, it's from Galicia in Spain. It consists of 4,000 samples collected from 2010 to 2023. It consists of 75 features. It's extremely sparse, which means that it has a lot of missing data. It has very high missing rate. And we took that data set and we restructured it into a 3D multivariate time series form, because the SATES imputation model, it imputes time series data. So the data that comes into it has to be time series data. But then SATES also requires us to introduce an artificial missingness, and usually that's by 10%. And by artificial missingness, we mean, so our data set, our Galician data set, it has a certain percentage of missing data. And we have a certain percentage of not missing data, existing data. That existing data, we have to introduce inside of it another 10% of, we have to make it missing. Why? Just so that we can have the model can have some type of ground truth, so it can be able to learn what to predict and what not to predict. So this results in our Galicia dataset in having a very high missing rate, which is 98 to 99% missing. And just for comparison, this is not used in our work, but just for comparison, the SATES paper itself, this is another model presented by other researchers. They use in their paper a dataset called PhysioNet. And that by itself, after also its 10% artificial missing rate, it also has a missing rate of 80 to 82%. So our data set has even higher missing rates. But an important aspect to note is that our data set is transposed in comparison to the PhysioNet data set. So SATES is basically, it consists of 2 DMSA blocks, which are diagonally masked self-attention blocks, and those 2 blocks, one of them learns from the data itself the correlations between the features in terms of time, and then the other block learns the correlations between the features themselves. And there are a lot of parameters here. These were guided by the paper itself, but to reach these parameters, there was a lot of trial and error, but it is in general a very large and heavily computational model. So when we trained SATES on, SATES on our Galician dataset, just also for comparison, this was the performance of SATES itself on our dataset versus their PhysioNet dataset. So there was an improvement on our dataset, but that's likely due to the different nature of our dataset. Again, it was transposed. And then after the SATES model was trained, we passed the dataset itself, the complete dataset. We inferred the imputed dataset out of the trained SATES model. And then that dataset was flattened to 128,000 samples. The prediction models that we used here, we used these different prediction models to predict these different water quality indicators, and this selection was guided by related works. So related works, various related works use these different prediction models to predict these different water quality indicators, so we followed those same lines. So our performance metrics, we use 3 performance metrics. The first is the root mean square error, which is sensitive to outliers, and the mean absolute error, which is not that sensitive to outliers, and then the coefficient of determination, which represents how well our model learned the variability in our data set. And we would like the RMSE and MAE to be closer to 0 and the R squared to be closer to 1. So these are our results. These are the 3 models used to predict pH, for example. The yellow is RMSE, and the blue is MAE, and the green is R squared. As we can see, SATES overall performs better as an imputation method, regardless of the data model, the prediction model itself, even though attention improved the performance just a little bit for pH prediction. In regards to dissolved oxygen prediction, for example, we used a lot of prediction models here. Those first 4 were just normal vanilla deep neural networks, which performed very badly. But then we had an LSTM and an LSTM with a Savitsky-Goulet filter, which is just a smoothing noise filter. And those in general performed much better than the first four. And until now, what we can learn is that for different models need different predictors need different models to be able to accurately predict them. So there isn't one model that's good for all of them. So that's the first note that we note. And then we have, for example, the prediction of total ammonium. This was a very difficult indicator to predict. It had very low performance in comparison to the others, but still SATES, as an imputation model, SATES was still provided the best performance. Then we have biological oxygen demand over 5 days, in which also SATES performed the best over all the metrics. These are the conclusions. My time is over. Should I just complete the conclusions? Okay. Thank you. So the conclusions of this work is that, first of all, the imputation choice affects the performance of our models, of our prediction models, very strongly, and that traditional methods such as median imputation or KNN imputation, they perform sometimes well and sometimes, but most of the time, not well in the prediction of different water quality indicators. And usually, when we want to select a method, we want to select a method that is robust over a lot of different predictors, so it doesn't just like perform well over one predictor. We want it to be more robust. We also conclude that SATES significantly improves prediction performance across most of the water quality indicators, and that recurrent neural networks perform better than normal deep neural networks and standalone convolutional neural networks. And for future work, we would explore relationships between even more different water quality indicators and extend to other environmental data sets, so different locations, different countries, for example, maybe explore additional advanced prediction architectures. And one of the most important points is that to study the possibility of having a single multitask prediction model that can predict all of these indicators at the same time, instead of having one model or different models to predict different indicators. So that was me. Thank you very much.
Thank you. It is
Thank you.
a little bit remarkable that you used for work a data set from Spain.
Yeah, thank you.
I meant we don't have data sets in Egypt for water quality.
We do, but I had like a small fellowship in Spain. That's where I got the data set. Yeah.
The initial plan was to cooperate with the Egyptian ministry. We have already set up the contacts, but unfortunately Marwa went to 3 months of scholarship, so we started working on this. But I think we're going to apply this on the Egyptian government.
Yes.
Thank you very much for all the audience and for the comments, and Professor, thank you. Mohammed, good to see you again. Thank you, everyone. Thank you, ladies.